So we're going to be talking at this point about VPP Envoy integration. So improving the Istio service mesh. Again, because I just discovered QR codes this weekend and I'm very excited about them, you have QR codes up here on the screen for downloading the slides. And you've got the link up here on the screen as well. And this will be present at the end too if you don't happen to get it now. Also, feel free to tweet any pictures you take. Cool. So, we're going to start at a very high level here and work our way down, rather than starting at the bottom and working up. So, we're going to start at a high level, and we're going to sort of go diving down from orbit towards the Earth. And hopefully the chute opens. So I'm going to start, as part of this diving down process, with a brief history of service mesh. Now, this is heavily cribbed from an article that was written by Phil Casado. I'm putting the QR code up for this article because it was freaking exceptionally well done in terms of how he broke things down. So if you look at the evolution of services, in the beginning, conceptually, what you have is you have two services that want to talk to each other. And way back in the beginning, when we hadn't worked out that we actually wanted to put things like flow control and congestion control and everything else into some protocol in the kernel, when you would build your services, in addition to having the business logic for them, you also had to do all that sort of work inside your service, which was a huge amount of work and a massive pain in the ass. So time went on, TCP and UDP came up, they got moved into the kernel stacks, so now your connection protocol stack is living in the kernel. You have a standard API to it. You're back to just doing business logic in your services, which is marvelous. And it was nice for a while, until we discovered there were other kinds of things we wanted to do. For example, service discovery and service routing. Some people will also talk about short-circuiting, circuit breaking in here. It turns out that if you actually try and list all the things that have come up this way, there are a lot of them. So again, you start out building these into your services. But as you get to a large number of services that are trying to do this in a similar sort of way across an entire system, building it in per service gets to blow really badly. So we did what we always do. We rolled libraries to put into our different services, so at least we're trying to do it in a consistent way. This was a little bit better, still not great. And at this point, somebody had a really smart idea. They said, what if we just put a proxy in place and let the proxy handle the service discovery and service routing? This was a huge step forward, which led to people thinking an even more granular thought, which is, if a proxy is good, what if we give every service its own proxy? And they called this the sidecar, because it's a sidecar to your service. Which led to a very fundamental observation, that if you look at a system where you have a bunch of these services and their corresponding sidecars, and you have these graphs forming among the sidecars, what you really have is a mesh of services, which is where the term service mesh comes from. So service mesh, interesting idea, kind of academic for most people, until Istio comes onto the scene. So with Istio, a few things happened. The first one was Envoy became the sidecar. Envoy is a high-performance proxy written in C++, came out of Lyft, where they're actually using it in production, as are quite a few other people at this point. Does a really nice job of doing all the things that you want to do in a sidecar, and so that ends up being the things that people have standardized on as we move towards service mesh with Istio. So now you've got Envoy as your sidecar, and you've got all these service mesh sidecars. And the question immediately arises when you have large numbers of things that you're trying to manage, managing them independently and manually becomes a burdensome activity. And the good news is we know what to do in this situation. We are network people. You introduce a control plane. In this case, Istio is your control plane that manages all your various service meshes. So you can express into Istio a global set of policy about what you want, and let it deal with configuring the specifics down to each instance of Envoy in order to make that a reality. So from here on, we're going to go a little bit lower. Now we can sort of see the outlines of the fields as we're plummeting towards Earth. So we're going to talk a little bit about how sidecar traffic flow works specifically in the case of pods in Kubernetes. So let's say you have network traffic that is destined for your pod. So the way this works is you have a bunch of redirect rules and IP tables that will redirect all of that traffic to the Envoy proxy container. So if I'm trying to reach the pod and I've got an app container listening for the port I'm trying to reach, my TCP connection does not terminate on that app. It terminates on the Envoy proxy container, the sidecar, which then proxies it to the app over the pod's localhost. So for some of you who saw the brief review this morning that I did, you may recall that every pod has its own localhost. This is how Envoy communicates, the TCP communicates with the app, having done its proxying behavior. And then when the app wishes to send network traffic out of the pod, that gets redirected via localhost to the Envoy proxy. So if I'm an app at an Envoy-enabled pod with a sidecar, and I try and reach out to google.com, I don't actually get delivered there. I get delivered to my local Envoy proxy, which then figures out what it's going to do. And the same is true for any other service that I'm trying to reach. And then from there, that gets proxied out to the world. Yes?
So I'm not actually an expert in Envoy. I see an ambiguity problem here, right? If I try to go to google.com, and it gets redirected to localhost, which is the way it has it.
Yep.
And then I get another connection to Microsoft.com, which gets redirected to the proxy,
Yep.
to localhost.
We'll just go on and put it next to you again.
I'm sorry. But how does the Envoy proxy know whether an incoming connection that got hijacked from the, or rerouted, retargeted from the app container was supposed to go to Google or to Microsoft?
Ah, this is actually an excellent question. So basically, I'm going to overly simplify because Envoy is a vast space. But one of the things that Envoy does brilliantly is proxying of HTTP. And so you can literally tell that I'm trying to get to Microsoft instead of Google because of the URL that I'm trying to reach.
Because of the host header.
Exactly.
Okay.
Right. And this is true just generally across the board. You have a ton of information in your HTTP headers that can be used to make decisions about routing traffic, not just even at the level of URL. Some of the things that people do involve having example.com/bar go to someplace different than example.com/foo.
Yeah, the path is in the request, and the host is separately in the request.
Right. People have even started doing things where they will match against cookies to be able to redirect particular users to different instances of services.
Now, I've also heard people talking about Istio handling layer 4 traffic rather than layer 7.
It can, but in the cases, so Istio has a set of capabilities, some of which Istio uses, some of which it doesn't. And Istio, Envoy also gets used as sort of an ingress proxy, where you have a big proxy in the sky instead of a sidecar. So there are many use cases for Envoy. It is capable of doing basic L4 TCP proxying. But you get to sort of the fundamental point that you can only proxy for what you understand. And so you do wind up with that moving into the mix. So if you're not doing HTTP, it has to be possible to differentiate what you're doing in order to proxy properly. So, as you saw earlier today, VPP has an extremely scalable, extremely performant, extremely efficient user space TCP stack. And that's just one of many things that VPP does very well at lower levels of networking. Envoy and the service mesh guys do a lot of good work for L4 through L7. VPP currently does a lot of good stuff for L4 through L2. So we can marry those up and look at the kinds of things that can be done to enhance Envoy with VPP integrations. So imagine again, network traffic comes into the pod. In this case, use the VPP user space host stack for that traffic going into Envoy. We're currently working with the Envoy community on direct, what I call opportunistic integrations of Envoy with the VPP host stack. And what I mean by opportunistic integration is if you have VPP available and you choose to use it, then this kind of thing can happen. Otherwise, you get exactly the behavior that you expected before. So from there, Envoy again wants to proxy things. Now, hopefully, with some of the things you saw earlier with DMM and with Florian's talk about the host stack, we'll get at some point to the point where we can use an LD preload shim so that we can have everything going through the VPP host stack. That would be wonderful. But as a first step, we can have Envoy simply transmit that proxying behavior over localhost. Localhost in Linux has a lot of optimizations because you know that if you're going out over localhost, you are never leaving the box. And that makes it possible to do a lot of useful things. Then again, network traffic out of the pod. This is probably in the short term going to have to be redirected via IP tables until we get to that point where we can LD preload shim the apps. And then you can proxy out over the VPP host stack again. What this means is that for your outgoing connections to the outside world, you get very, very good performance. And you can use the Envoy proxy as the capture point to proxy this behavior across to the existing apps. By the way, feel free to interrupt at any point for questions, which goes for more than just Mike, although we love your questions, Mike. So, interesting ways to look at this. So we'll look at this from a slightly different angle. So we say we have traffic coming in from VPP, and we wanted to get it to Envoy. We were talking about that integration again, and as you saw in Florian's talk earlier, we can use the VCL API and shared memory. So if you're just talking about traffic coming from the outside world to Envoy, you can get shared memory between VPP and Envoy for the actual data that you're passing across. Now, if on a single node, you're running a second instance of Envoy to a different app. In this case, just as you saw with the cross communication between two apps on the same server, where we can set up a shared memory FIFO, we can set up the same kind of shared memory FIFO directly between Envoy instances. Now, what this means is if I'm running two apps that happen to be on the same node that are using an Envoy sidecar, the connection between those two Envoy sidecars is shared memory. It operates at the speed of your memory bus, which is a huge step forward over anything that has to actually traverse PCI to a NIC. Any questions so far?
Are you going to get to pods or namespaces, right? If you're in separate memory namespaces, then...
Absolutely. So when you have different pods, you have to use the namespacing feature in the host stack because you don't have the kernel namespacing feature available to you inside VPP. And you need to make sure you have the proper isolation of each pod. But if pod 1 and pod 2 have requested to be connected to transmit bytes, then it's appropriate to set up a direct connection between those two pods just for that session, for that single socket connection, if you will. So I wanted to pause to do a brief Envoy architectural overview, very, very brief. There are a few things that it helps to think about and understand about what's going on inside Envoy architecturally. So at a very base level in Envoy, you have listeners. These are things that are listening on an IP and a port, and they tend to be TCP. There's some work going for UDP listeners, but right now you basically have TCP listeners. And this is how you say, okay, great, we're going to listen on this particular port for incoming connections. Those listeners, when a connection comes in, will hand it off to a list of listener filters. Now, what a listener filter does is it annotates the metadata associated with that connection so that you can do things like, for example, when a connection comes in and it's been munged by IP tables, you can recover some of the original information that IP tables has munged, and you could have the orig destination listener correct, for example, the destination. So if something came in and it got munged around so it's coming into a different port on Envoy than it was destined to on the app, you would like to have somebody fix that metadata about your connection so that your app is none the wiser. So you set all the proper headers in HTTP that indicate what things are happening where in the correct way. Then, after you've gone through the listener filters, when you start getting things coming in on L3 or L4, you hit what they call the network filters. And these are looking to see something about the actual content of the data that you're dealing with. So this is where you would run into something like the HTTP manager that can figure out, okay, what's coming over this socket is HTTP. And therefore, we should treat it that way, and we should figure out how we're going to route it based on HTTP headers and the configuration that we've received dynamically for them. And then once you've figured out that you're dealing with HTTP, again, you get a list of HTTP filters, like HTTP routing. So you sort of see this pattern emerging as things are passing up layers of abstraction, and you get a list of filters at each layer that get applied to the thing that's being passed up. So, yes?
I'm sorry, I wasn't quite clear on. So what do the HTTP filters actually do?
So you get an HTTP request or response. They will munge those headers. They will open connections to the places that you should be sending them to. They will deal with the responses, possibly munge the headers of the responses, and redirect the stream back to the originating requester. That kind of thing.
Thank you.
Exactly. And it turns out you can do all kinds of other things that people care about, like header compression, et cetera, in those filters as well. There's a whole laundry list of them.
What if it's an HTTPS connection?
So one of the things that you can actually do at lower layers is you can actually handle the TLS piece. Envoy typically terminates the connection and therefore terminates the TLS so that it can see in clear text what it's dealing with. Yes?
Envoy uses OpenSSL or something like that.
It uses boring SSL.
So the use of Envoy, is not transparent to the developer. The developer has to somehow get the right certificates into Envoy. And
So typically the
configure.
way that's done is there's decent integration with the Kubernetes secret mechanism so that you can actually manage your certificates in that way. So yes, there needs to be a way for certificates to be managed, and there has to be a way that can be relatively easy.
But then all the time the assumption is Envoy reads the data.
Yes. If it's going to do HTTP proxying for you, it has to, right? If it's not terminating the TCP connection and then it's terminating the TLS, it can't really see to do what it's doing. But a very typical pattern is terminates TCP connection and TLS, opens new TCP connection, possibly with TLS, munges traffic between them, and you may get a multiplexing behavior where on a single TCP connection coming in into Envoy, I might send a bunch of requests because they've got the same hostname on them, but coming out the other end, they're being routed out to a bunch of different possible services.
But
Yes.
still on that point,
Uh-huh.
Envoy shouldn't care too much then if TLS is handled before it.
Oh, not at all.
Okay.
No. In fact, one of the things that we've actually had discussions with the Envoy community about is the possibility of doing TLS offload to VPP, opportunistically again, because in addition to the fact that we can do it fairly efficiently in VPP, with the work that's going on with hardware offload, it turns out to be substantially simpler to do hardware offload for crypto hardware from a single vSwitch container than possibly 100 Envoy sidecars. It's just a much smaller amount of complexity to do that in one place. So this sort of brings us to the question, how do you go about doing this integration, right? So what are the integration points in Envoy, and how do we actually get there? So you start by saying, okay, what are the conceptual things that we're doing, right? So one set of conceptual things is you're doing socket reads and writes. You're getting data that comes in, you're reading, you're writing data out. And it turns out that Envoy already has a modular pluggable thing for this called a transport socket. You can configure that you want to use a particular transport socket implementation for your reads and writes, and it will handle that for you. So that part is simply a matter then of writing a transport socket plugin for VPP. But then you get a whole set of things around socket management, right? There's bind, connect, accept, God help us save us from the socket ops and the IOCODLs, all these sorts of things. And in this space, what you really have is they have a socket object in Envoy, but unfortunately, a prominent method in the socket object returns is a method that returns the file descriptor, and much evil ensues, because yes.
Does it ever check that it's a real Linux file descriptor?
Not that I'm aware of, but it turns out that we're not the only ones who care about this problem. The folks from Google who are doing quick implementations also have the problem that passing around raw file descriptors is not great for them. So there is a strong desire to move away from this pattern in the Envoy community.
Okay.
But it currently fans out through a bunch of different classes in Envoy. Addresses, listener sockets, buffers, others, where a variety of places will take advantage of the raw file descriptor, which is a totally reasonable thing to do in a world where you're just accustomed to dealing with a Linux kernel. But as you expand your horizons, becomes problematic. So that's really a big part of the crux of the problem, is rooting out that FD call that returns the file descriptor and the various places that use it. So, good integration patterns in this situation. So first of all, bad integration patterns. Bad integration patterns involve hacking the shit out of stuff until it works, because that usually ends up with a piece of code that's not actually usable for anyone else, including typically the people who originally were using it. So a good integration pattern here is to start with the Envoy core and build in a point of modularity in the Envoy core that will allow you to plug in some extension that works for you. So a good example of this would be doing that core extensibility. You can then build a VPP plugin that plugs into that extensibility point. Other people can build other plugins that plug into that extensibility point. It's just good hygiene. So, for the socket read and write behaviors, we already have such a pluggable point in the Envoy core with the transport socket. It currently gets serviced by a raw transport socket plugin. There's also a TLS transport socket plugin. The mount point was put there because various people have their own transport sockets that are not in the Envoy repo that they plug in there as well. And so what we've done there is to produce a VPP transport socket that can be plugged in there. So socket management gets to be more interesting because we don't have the right points of modularity there right now. We need to root out that raw file descriptor call, where you get the file descriptor, and fix the points that it's consumed, and incorporate the things that we need to make that work into the socket object. But once we do that, we also then have to write the Linux socket plugin so that normal behavior works correctly. And then we can write the VPP socket plugin to plug into that as well. Yes?
Bad idea.
Which one?
Can you just... no, bad idea.
Oh, you have a bad idea.
Coming right now.
In here, I thought I hadn't thought this all the way through.
If they don't ever check that this is a real file descriptor, why not use an N32 as the identifier, and then Linux knows how to handle it, VPP would know how to handle it as well.
So there are a couple of things that are problematic about that. So one is we're trying to come up with a solution that works for the broader community. And the broader community has a broader set of problems that are in the same direction of the problem that we have here. A second thing that happens is that there's sort of a number of ugly places where people make various calls on that file descriptor in the code base, like bind, that have to be rooted out anyway. So if you're going to have to go root those out anyway, you might as well pull them together into an object where it's handled cleanly. But no, it's not such a dumb idea. It's exactly the right first glance idea, right? It just turns out that when you dig deeper, it becomes more complicated, and then more complicated, and then you find yourself in the hacking shit up game again. You discover that you suddenly have 15 modularity points where with a socket object you would have one. We really don't want to write our own buffer implementation, for example. And then I also mentioned there's an interest on the part of the community in doing this for quick, where you could essentially also say, okay, we're going to produce something that has socket-like behaviors, but that is actually doing quick instead. And then, I get back to this point, I mentioned this a little bit earlier. This is something we're trying to do with the Envoy community. We've been pushing PRs, having conversations, et cetera. And there are non-VPP community members that need work that is close to this as well. So the quick guys, as I mentioned, they need something in this direction. And we've been asked to also work with the Cilium folks because they also have opportunistic extensions that they would like to do. And I suspect the Cilium guys probably don't have the same socket issues we do, but they do have some extensibility things they want to do in this space. So definitely worth talking to them about it. Cool, so that's the basic talk on where we are right now with VPP Envoy integration. We've got sort of the first piece done with the transport sockets. We've figured out the strategy, I think, for moving forward from here. And so now it's a simple matter of code at this point.
That PowerPoint to code conversion engine, how's that coming along?
Terribly. Which is funny. I mean, I may not have mentioned before, I'm second generation software. I am a coder like my father before me. And going all the way back to the early 70s, you had people who were trying to write compilers that would take a language and compile it to do what you meant it to do, instead of what you actually asked it to do. Apparently the result was PL1. This turns out to be a terrible idea. Don't do this. So, really quickly again, we do have the QR code if you'd like to get the slides, so that you can go download them, use them, abuse them, and recycle them. Please do feel free to recycle any of my slides. I care not about attribution. I care slightly about color palette. Please try and pick one that's not terrible. So there you go. Any other questions before I conclude? Yes?
Moving forward, where do you see TLS?
So I think there are huge advantages to a hardware-accelerated TLS living in VPP and having Envoy essentially, again, getting to your point about certificate management, I expect Envoy is going to stay in that game. Having Envoy, when VPP is available, offloading that to VPP and handing it the proper certificates to do the job there. I think that makes a lot of sense. I think that other members of the Envoy community will be more convinced by running code that does something interesting and useful there, but they are tentatively willing to entertain the possibility that this might be a happy thing. Any other questions? Yes?
In terms of acceleration, I know Intel has many libraries, pattern matching, and so on, like sliding pattern matching. Does that make sense to accelerate pattern matching processing in Envoy with this?
That very well could make sense. I think you're talking about the quick scan stuff. Am I remembering the name correctly? Hyperscan. And if I recall correctly, the Hyperscan guys were good enough at that in software that you stopped doing it in hardware. That would probably make a lot of sense. That's not directly in the scope here, but it's definitely an interesting thing to look at. Any other questions before we move on? Awesome. Thank you all. You've been a marvelous audience.
Cool. Thanks, Ed.